Okay, so this is homework 5, part A, and so we want to derive the Gibbs phase, right? And then we want to find the difference for. So the first thing that we want to do is, let's say we have a thing. Let's say we have a system, right? And in the system, there's 3 different phases. So we have vapor, and then we have liquid at alpha, and then we have liquid at beta, right? So when you have something like this, we can say that the property, so we could say that the phases are P, right? And so P equals how many phases are in this multi or phase. So in this one, right? Because there are 3, there's 3 phases in it, right? So we know that there are 3 phases. And what we want to do now is we're going to find the chemical potential of these 3 phases. So the first thing we want to do is chemical potential equals. So it's going to be derivative of Gibbs free energy. So Gibbs free energy, the derivative of the Gibbs free energy is going to be the number of moles times the number of moles per Gibbs free. So, and then it's going to be divided by the change in. This is all going to be the change of moles. And then this is all going to be in respect when temperature, pressure, and a certain amount, so a number of moles J is constant, right? So this is what we're working. So why this is NJ because there's a number of portions, a number of components that are going to be in our systems, right? So these are going to be 3 different. So let's look at our components of our system. So let me draw. The vapor or alpha. And so let's say we have partial. So there are partials in each 3 of these, right? So we're going to have y1, y2, y3, yada, 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 and then yc, right? Because how many components are in this. So the components of this equals, right? Components. And then we're going to have y alpha. And then y of alpha 2 and y of alpha 3. Yada, 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 until we get to a component C, right? So all the components equal C. And then we're going to do the same thing. We have y beta, 1 y beta, 2 y beta, 3, and then we got it from y beta C, right? So it's, again, so all of these are going to be equal to amount of C, right? So what are we going to do with this? Let's see. So the first thing that we want to do is that we know that all of these have different properties. If you think about it, we are going to look at our intensive variables. Intensive variables. So intensive variables equal pretty much are they don't depend on the size of the. So what does that mean? So that means if whenever how big this system is, it doesn't depend on the size, right? So if we think about these, right, these partials not depend on the size of the system. They're going to depend on the property of the phases because there's a component for each phase, right? So they don't depend on how big the system is, they just depend on the phases, right? So let's think about that. So we're going to do phase, right? Because they all depend on phase, and then we're going to do our C, right? We're going to find out how many components we have, right? So let's think about all of these are C, right? They're all tied between C, which is C, right? So how are we going to do this? What partials can we put down? How are we going to represent all these partials? Well, we can do C minus 1, right? C minus 1. So C minus 1 is going to be the sum of all of these minus the remainder, which is 4. So this is going to tell us all of these components for each phase, right? So this one is C minus 1 and C minus 1, right? And then the next thing that we want to do is add plus 2. Now, why we add plus 2? It's going to refer to our temperature and our pressure, right? So we come back over here to chemical potential, right? We see that there's temperature, pressure, and then our components of the mold, right? So we have that represented right here. Okay. So the next thing we want to do is now that we have this, and this is going to equal our intensive variable of this, right? So now, what we want to find is we're going to figure out what this is an equilibrium, right? So when we have a multi-phase system and they're at equilibrium, how are we going to do this, right? So let's think about this. So if they're all at equilibrium, all of these chemical potentials will be at equilibrium, right? So let's write this down. So we have equilibrium, chemical equilibrium at the vapor equals the chemical equilibrium at the outlet, right? These two are going to equal. And what are these equal? This is C, right? You know this because there are C amount of components, so which will be C, will change in the right? And so we also know that chemical potential of beta, the chemical potential of the alpha. Alpha is going to be beta. Right? So this is also going to be because about how many components are C components, and then there's C equation. So we also don't have to put our vapor, right? Our vapor and our beta into each other because we already have this one right here. We have a alpha here and alpha here, and while they equal this, we're going to assume pretty much is something, and so we'll be redundant. That doesn't happen. The next thing that we want to do is think about this. All these chemical potentials are, right? So if you think about this, these are going to be times a phasor, right? We're going to do a phasor. We have to do minus 1. Why we do that is because one of these equations, sometimes they're going to equal each other, right? They're going to cancel out. And so we need to account for that by making a minus 1, right? So we don't want it to be redundant of, well, there's one of these that equal each other, so we don't want that. So we have to subtract it. And so this is going to be the equivalence of our chemical potential, right? So these are going to be all equal each other, and this is going to be our chemical potential. The next thing that we want to do is, so now we're trying to find the Gibbs phase. So we have here, and we have this here, so we're going to subtract, right? So we're going to do over here. So P minus 1 plus 2. So this one is going to be our equation for the intensive variable minus the equilibrium of our potentials, right? Of our chemical potentials. So we subtract these because if there's any similarities between them, so if there's anything that's the same, we can subtract them out and cancel them out because again, they're going to be the same. We want to find just the amount of variables, right? If there's the same, that there's you just want the variables, you just want the difference to them. So we have to subtract, right? So next thing that we want to do is we're going to distribute P and we're going to distribute Q. So we're going to have PC minus P plus 2, and then bracket, and then we're going to have PC minus, right? So then we're gonna cancel these out, right? They're gonna cancel out, they're gonna cancel out, right? So then we're gonna have, I've distributed the negative, so it's gonna be C minus P plus 2, right? So now this is gonna be equal our Gibbs phase equal our Gibbs phase rule, right? These are gonna equal our Gibbs phase rule, right? So next thing that we want to let's make this into a system. Let's put this into, let's say we have pure water, right? Pure water, pure H2O. And we're going to put this at the triple point. So how many components are there? It's a pure component of water. And then the triple point, that's at the triple point when there's all three phases close together, right? So now let's plug this into our equation right here. So there's one component minus our triple point, which has three phases, plus 2. So now let's think about this. So we do this here, so that's going to be negative 3 plus 2. That means there is 0 degrees of freedom. So does this make sense? Okay. So let's have our graph. Pressure, temperature. Over here, right? So here is the triple point, right? So what it's saying is that there's no degree of freedom. That means there's going to be no variable change. So our pressure and our temperature are not going to have to change, right? So there's only one pressure, one temperature. That means that you have the triple point, right? So I have here. So when I have a pressure, it has to be this pressure, it has to be this temperature. There's no change because there's only one like singular pressure, one singular temperature. That means there's 0 degrees of freedom. There's nothing you can change about temperature or pressure to change it. So this makes the next one that we want to do. So let's say we still have pure water, pure component of water. I'm saying we're at the triple point. Let's say we're at the volume. Let's say we're at a vapor and right. So this is 2 phases, one component, and let's put this back into our phase. There's one component minus 2 plus 2. This point equals 1 degree. Okay, so does this make sense? How does this work, right? So put it back in. So we have pressure, we have temperature, goes up, right? So it's saying that there's 1 degree of freedom. So let's say the vapor, and this is a liquid, right? So if you want something that's on this like equilibrium, right? Equilibrium line between the vapor and the liquid, and the new pressure. So we're going to start with the pressure. Say you want this pressure, right? It's going to give you a corresponding temperature, right? So to be at this equilibrium curve, if you pick a pressure, you're going to have a corresponding temperature, right? So the same thing goes with the temperature. Let's say you want to do it at a certain temperature. And right here, you're going to get a certain pressure with that, right? You're going to get a certain pressure. So you can input a temperature or a pressure, but it's going to give you a certain value of a temperature or pressure. It's going to have an output. So you're going to put something in, it's going to give you an output. So that means you can only change one thing, right? So you have 1 degree of freedom, but it's going to give you something else. So you can't change the pressure and the temperature to something that you want. You can only change one. If you want to keep these 2 things. That makes sense. So now, let's say we have a mixture of ethanol and pure water, right? So H2O and CH3, OH. Okay, so let's say we have ethanol, right? This has a mixture components. There's 2 components, right? And let's say we're in the phase of vapor. Let's put it in 2. The 2 and 2. So let's put this into our equation again. So 2 components minus 2 phases, right? Plus 2. So this is going to equal 2. The thing we have 2 degrees. So now let's draw this out. This kind of makes, if this makes sense. So we have a system that has vapor and our, right? So in our phase that we have our liquid, we can change the temperature, right? We can change the pressure. So these are some obvious changes to make, right? But since there is a mixture of two, like there's a mixture of two compounds, right? We have pure water and we have that. There's going to be a partial, we're going to have a partial mole of both of them, so X1 and X2 in both of these phases, right? So let's say instead of changing our temperature, let's change one of our moles. So X1, let's say we change one of our partials into that. So we can change it into this, and it's going to give us corresponding pressure, right? So we can do all of these. We can change 2 of them, because this is going to tell us what the second partial is. And this is going to tell us what the pressure is as well, right? So that's 2 degrees of freedom, and it's going to give us multiple outlets, right? So that makes sense. So that is going to round out part A.